Okay, welcome everybody to another GEOTOP-A seminar, and this time is Bastian Rieck from Helmholtz campus in Munich. And shall we learn about curvature for graph learning? Bastian, to you.
Thank you very much. It's really amazing to talk about this because it's just something that started developing as an interest for me a couple of months ago, and I'm really glad to be able to share this with all of you. Now, I want to start the presentation with a very mixed audience in mind, so I'll talk a little bit about some graph learning paradigms first, then I'll talk a little bit about what curvature means, and then how to extend this to graphs, to hypergraphs, and then I'll also show you what we can actually do with this in these contexts. Now, after every part, I'll do a brief pause, of course, and this will give us some time to collect questions and have maybe a mini discussion if that is of interest. Otherwise, since I also can't see the audience, I'm afraid I have to say, please just feel also free to interrupt me if there's something that needs to be discussed at a certain point in the presentation. But with that being said, let's start. Now, if you're not familiar with the field of graph learning is one of the rapidly developing fields in machine learning research at the moment. And the central object of graph learning is, of course, as you might guess, is the graph itself. And the goal of graph learning is to address typical tasks that involve the graph. For instance, one of these tasks could be graph classification itself, or node classification, or edge classification. So you get one of these objects and you're asked what label it should have. There are also regression tasks for the same object, so for graph nodes and edges respectively, with predicting a certain parameter or a certain property. For instance, the solubility of a molecule or the molecular mass. All of these things would be typical regression tasks. Then there's, of course, the edge, or sometimes also called a link prediction task, where your goal is to be given the graph and then you predict new edges. So maybe people that should know each other in a social network, something like this. And finally, there's also the quest, or the question, I should maybe say, of graph distribution comparison. So the comparison of graphs along different axes when they are sampled from some kind of underlying distribution, for instance, by some experiment. Now, these tasks typically have to involve some kind of graph representation, and the ordinary representation as a graph, as a set of vertices and a set of edges, is unfortunately not strong enough here, because one of the issues that we have when we're dealing with this in a machine learning setup, I should say, is that two graphs typically have a different number of vertices. So any kind of representation that we want to have needs to incorporate these differences in the number of vertices. This is typically, and of course in the number of edges as well. This is typically addressed by vectorizing the graph. So this is a special, I would say, machine learning speak for saying we take some map F and we learn this map such that the images of both graphs of G and G prime are both part of the same high-dimensional vector space. Regardless of the actual size of the graph, you try to map all of these graphs into there. Now, this type of map, of course, it needs to have some special properties. So one thing that you will always encounter in the graph learning literature, it's not super important for this talk, but I want to mention it because it gives this kind of a holistic feel for the field, is that this map needs to be permutation invariant. That is nothing else but saying that it needs to be oblivious to the internal ordering of the graph. So if I change the order of vertices by just enumerating them in a different way, then the representation should remain the same. This is a normal requirement to ensure that you're getting the same outputs all the time. Now, let me give you a brief and very, I should say, almost shallow overview, no pun intended, because shallow appears here as well, of some typical algorithms for representing graphs. They will not play a very big role in this talk, but I think it's important to at least give some basic understanding of where the field where machine learning is headed in practice. Now, there are a lot of approaches that almost have a long history nowadays. There are these so-called shallow approaches, by which we mean that these are approaches that just solve one relatively simple optimization problem. The classical example would be Node2Vec, which uses an encoder-decoder optimization. There's also graph kernels, which are essentially, if you're familiar with this terminology, reproducing kernel Hilbert space feature maps. And there's, of course, also embeddings based on the Laplacian of graphs. And if you tailor those correctly, then you end up learning permutation invariant representations as well. Now, the recent start or the recent revolution has been this deep approaches in machine learning research. So deep learning, everyone knows that, right? But deep learning also led to new ways of looking at graphs and representing graphs. For instance, there's graph convolutional networks, graph isomorphism networks, graph attention networks. You can kind of see some nomenclature structure in there. All of those have one thing in common. They are all based on the idea of taking a graph and embedding it in some kind of higher dimensional vector space. And the way this mapping is done, this depends. The way and the expressivity in which this mapping is done is also dependent on the architecture. One other common underlying paradigm that most, if not all, the relevant architectures share at the moment is the so-called message passing paradigm. And this message passing paradigm will give us some hint as to why curvature might also be useful to study in the graph learning context. So I'm including this as a kind of motivation for me and as a kind of pole star, if you will. The concept of message passing is relatively simple. You just suppose that every node has some kind of message, in this case x, y, and z attached to it, and this message is a vector in a same high dimensional vector space, and these are then aggregated using the neighborhood of a given node and using a function such as a sum, a mean, or some other permutation invariant functions. So for instance, we take a look at node D here in the middle, we take a look at node B and its message X, at node C and its message Y, and at node E and its message Z, and then we aggregate all of this, so we solve some kind of function or we learn some kind of function that aggregates X, Y, and Z into a new formulation. So this is of course a very simplistic view, but this almost explains at least a lot of what is going on behind the scenes in current graph machine learning technologies, in common graph machine learning algorithms. Again, this is not something that we will directly leverage, but we will leverage some kind of conceptual moral from this. Namely, the moral that I learned from this is that we can obtain informative global representations by just doing these local measurements, by just doing these local aggregations without going further and deeper into the graph. We can already form a picture of the graph and form a representation of the graph that is useful to address some of these graph learning tasks. And one of the nicest invariants and nicest concepts in topology I know of, and which is inherently local, is of course curvature. So this is the foundation for this excursion into curvature for graph learning research. This is already the end of the first part. It's a very brief part, I know, but maybe are there any questions at this point already, or some comments? All right, then I'll continue, and maybe after the next part we'll have some more discussions, because this is also a very brief introduction to a subject, in this case curvature, and by necessity, of course, I will miss a lot of the interesting things, but I'm trying to prepare us for talking about curvature in the graph setting. Now, what is curvature? Well, let me first give you a very intuitive description. So I'll try to keep the formula in check, so that they only appear at the places where we actually need them, namely later on when we talk about graphs, because otherwise we would have to talk about Riemannian geometry, and that would take a little bit longer. But the motivation, as most of you, all of you, some of you might know, is that curvature wants to characterize how curved an object is. And this object can be a surface, a manifold, a topological space, and so on. Curvature can also be either considered an extrinsic property and an intrinsic property. There's a famous theorem by Gauss that tells you that the Gaussian curvature, so the product of the principal curvatures, that this is actually an intrinsic property of the surface, so it does not depend on a specific embedding. And of course, classically speaking, as a topologist or as someone who is interested in applied topology, I would say I care a lot more about intrinsic properties of the data, because it is possible that my given representation of the data does not really fit with the task at hand. Now, the classical examples of Gaussian curvature regimes are the regimes of negative curvature, which are hyperbolic surfaces, zero curvature, which are flat surfaces or planar surfaces, if you will, and positive curvature, which are spheres. And I'm mentioning those here because these quintessential model spaces, they will reappear in a kind of warped form when we talk about graphs later on. Now, why is curvature actually useful? Well, if you already work in curvature, then feel free to ignore this, of course, but I want to give you also an inkling for those of us that are not directly familiar with the field. There are certain things that were mind-blowing for me at the beginning when I learned about this for the first time. So in the manifold setting, for instance, we can use curvature, which is a local quantity, right, to nevertheless provide information about the global characteristics of a manifold. So there's, for instance, the famous Gauss-Bonnet theorem, which essentially relates the curvature or an integral over curvatures and over the boundary, of course, to a purely topological characteristic, namely the Euler characteristic of this manifold. So this is already a very interesting and super deep result that I hope I'm doing this proper justice in appreciating it here, because I find it astounding that on the left-hand side we have an integral over some kind of local property. On the right-hand side we have a purely topological property, and nevertheless this still works out. Likewise, we have the famous Bonnet-Myers theorem, which states essentially that if we have a bound of a curvature, so we assume that the Ricci curvature, without going into the details here, of our given manifold is at least as large as that of a d-dimensional sphere, then we have a bound of the diameter, and we moreover know that M must by necessity also be compact. That's also a very exciting theorem for me, because it again relates a very local characteristic to some global properties of our object, in this case the diameter. Now, at this point, this is all I have about why curvature might be useful. Are there any questions or discussion points before we move into the graph setting?
Bastian, I have a curiosity.
Yes.
Maybe you can recall us if you know, but is any? It seems that the Bonnet-Myers theorem or result that you quote has some relation with the Milnor's theorem, the Milnor's bounds on total curvature and bridge number or other topological quantity. Do you remember if there is any connection between these two results?
Unfortunately, not by heart, but I would not be surprised if there were, because there are a lot of these very interesting results that relate certain, I would say, certain combinations or certain sums of curvature to certain other characteristics of an object. But unfortunately, I don't recall anything specific from Milnor now. I'm sorry about that.
Is an interesting point, because in actual fact, so we know not so many results that are connecting or relating global geometry to topology, and it's always very interesting to find out if we know something more about this. Anyway, thank you.
Yeah, no, absolutely. I couldn't agree more, and this is also what leads me then into these excursions for the graph setting, because there we are dealing with a very alien space in some sense, because we almost always lose all our smoothness properties. But we'll see about that now in the third part, where I talk about notions of curvature in graphs. And I should state that I will try to give as many references to existing literature here as possible. as by necessity almost, and unfortunately, since it's a very, very big field, I might miss, of course, some important references. I'm really sorry about this in advance. For the papers that we will discuss subsequently, we have an extensive bibliography, and we try to really scour the literature for relevant results. But if I miss something, please let us know, and I'm really, really happy to incorporate this in the next version, either of the paper, of our preprints, or of course in these talks. But with that, let's start a little bit. Now, in graphs, we are in a little bit of a different world. So when we're dealing with a graph that I just consider to be a tuple of vertices and edges here, we assume for simplicity that this graph is connected. Then we see that these graphs normally lack maybe some kind of smooth structure, right? So in some sense, we could consider them to be a finite metric space, but there is not directly a beautifully smooth structure as with the Riemannian manifold. So this means that we require a different treatment and a different way of assigning curvature values, but they can still be motivated by the smooth case, of course. And in some sense, we can also see that they coincide. I'll briefly talk about two notions of curvature here, the Foreman-Ritchie curvature and the Olivier-Ritchie curvature. I must admit that the Foreman-Ritchie curvature, I'm including this only as a kind of baseline combinatorial comparison. I'm not an expert with Foreman-Ritchie, and I'm still kind of discovering the relationships here. So I would say the larger focus will lie on the Olivier-Ritchie curvature, in fact. Now, why is curvature useful in the graph setting? We'll delve into this a little bit more, but I want to already give you some hints as to where people have been using this. So there's a great paper by Topping and colleagues where they discuss these graph curvature notions. In fact, the Foreman-Ritchie curvature, which is why I included it here, in understanding certain phenomena when doing graph learning. Namely, there are certain phenomena that are very much undesired, namely over-squashing and bottlenecks. These are essentially information bottlenecks that make it harder to train your machine learning model on the graph. And it turns out that they can relate those bottlenecks, or the existence of those bottlenecks, to negative curvature, or I should say negative Foreman-Ritchie curvature, or even more specifically, a variant thereof. Then there's a recent preprint which I find very exciting, which is revisiting this concept, revisiting these over-smoothing and over-squashing issues, but using this Olivier-Ritchie curvature, which is very, very timely since I'll be talking about this for most of the rest of the talk. And finally, there's also some work by myself where we look into the curvature as a characteristic property for simplifying graph learning tasks or for enabling certain graph learning tasks. So I'll be talking about two recent papers. One is the Olivier-Ritchie curvature for hypergraphs, a unified framework. We'll be discussing this towards the end of the talk. The other one is a preprint on curvature filtrations for graph generative model evaluation. Both of those are, I would say, very much on the applied side. So we always use curvature, although in the case of the first paper, we also think about new notions of curvature and what that would actually mean for hypergraphs. Now, that being said, let me give you a brief overview of Foreman-Ritchie curvature. So Foreman-Ritchie curvature for an edge in the graph is defined as a combinatorial sum of the degree of the respective nodes plus the number of 3 cycles, so the number of triangles that are incident both on the respective nodes. So it's a very nicely calculable, very efficiently computable, I should also say, invariant of the graph. And as we can see, if we calculate this for this nice graph here, we can see that some parts get assigned low curvature and some other parts get assigned a rather flat curvature here. So it already gives us a way to look at this graph under a different lens. So we gain some more information. We gain information that is not necessarily related to the degree, because you can see, for instance, that these two edges here they have the same color, but these two edges don't. So we gain some more insights into how the local topology of the graph looks and how it branches and so on. This is the only thing I want to show about Foreman-Ritchie. You can also see that being combinatorial, you might expect that it might be limited in terms of expressivity. I can't say any specific results there, but I can only say that we of course want to move a little bit beyond that in practice. Now, What we want to look at here is actually the Olivier-Ricci curvature. So the Olivier-Ricci curvature of a graph with the shortest path metric and a probability measure mu v, which is defined for a node v, is given as this very complex expression, I should say, that uses the Wasserstein distance, a transportation distance between the respective probability measures, and normalizes that over the distance within the graph. This might look a little bit weird at first, so we let that sink in briefly. First of all, it is defined for a pair of nodes, so I and j do not necessarily have to be connected. This is one of the reasons why we have this distance-based normalization term in there, and the transportation distance term is put there in order to mimic the behavior of Ricci curvature in the smooth setting. Specifically, the Ricci curvature can be described, and this is due to Olivier in the paper Ricci curvature of Markov chains on metric spaces. This is a very good conceptual overview and defines all of these notions for the first time. Ricci curvature, or positive Ricci curvature, is defined by the fact that corresponding points of small spheres in a space are actually closer than their respective centers are. And the probability measure that we learn or that we assign to nodes plays the role of a very small measure of a very small ball in this graph space. And what I find astonishing about this is that it gives us a lot of freedom to define and set certain things up. We'll see how to open this a little bit and how to assign probability measures, how to choose them in practice, and so on. So I want to say that this was originally introduced though for metric measure spaces, but this notion of curvature by Olivier was then quickly also adopted for using it in the graph setting, since in some sense one can say that it is a kind of natural generalization of Ricci curvature to a larger class of objects, because you can always define probability measures under very mild conditions of your space, even in finite spaces, right? You can do this, and a distance is also almost always available even in finite metric spaces. So this is really very nice to evaluate in practice. Now, let me talk about some useful properties of this curvature notion without giving proofs, of course. So the first thing that I find very good about this is that there are certain natural lower bounds. So it's sufficient, in fact, to know the values of this Olivier-Ricci curvature for each edge, and then we know that all pairs of vertices are lower bounded by this value. This is already good to know. This means that we don't have to necessarily calculate it for all the pairs. We also have a Bonnet-Myers-like theorem, I should call that, because if we know that we have an upper bound and a lower bounded positive curvature in the graph for all the edges, then we have a statement that relates the local distance between nodes with a kind of jump probability between two of the probability measures. So specifically, if we take a Dirac measure that is centered at a specific node of the graph, and we calculate its transportation distance with respect to the first Wasserstein distance to the respective other probability measure around that node, then we call or refer to this as the jump probability, because it basically tells us how much are we away from a Dirac probability measure at a single node, how much do we actually jump through the graph. And we can see in equation 3 that this leads to a bound that is relatively remarkably similar maybe to the Bonnet-Myers type bound if we go to the extreme, if we go to the maximum. So if we have this bound for every distance, then of course we also have a diameter bound here based on the supremum of these values here. And this is also very nice because again it shows us that this Olivier-Ricci curvature notion has a local computation but has a global meaning in the graph. Now, how is this probability measure typically picked? There are a lot of options actually there, and I think that one of the things we should actually discuss later on, or maybe even consider working on, is how to pick different measures. But I would say the common practice is to define a version of this probability measure based on lazy random walks. So we take a laziness parameter defined by between 0 and 1, and then we define a measure that assigns this laziness to basically staying at the same vertex, or with the rest of the probability that is distributed uniformly among the other nodes, or among the other neighbors of the given node. This is done, I would say, maybe correct me if I'm wrong, or if you consider this to be different, but I think this is done because it's supposed to mimic the idea of curvature being a local property of a manifold. So you don't go deeper into the graph because there's no need to. You want to study the local properties. Interestingly, and this is due to Lin and colleagues, there, with this definition, we can see that, first of all, this Olivier-Ricci curvature is nicely bounded between -2 and 1, and we get a Bonnet-Myers type bound of the form that the diameter is less than or equal to 2 divided by positive curvature, in the positive curvature realm, if we have a positive curvature bounded from below. Now, there are some canonical examples that I want to show you. So I told you that the canonical model spaces, they still appear or reappear. In Olivier-Ricci curvature, this hyperbolic space and the planar space and the spherical space, they become different graph examples. In our case, these are a tree, which represents the hyperbolic regime, a grid graph, which represents the planar regime, and a fully connected or a clique graph. It's not fully connected here, but I try to make it as fully connected as I could, represents the positive curvature regime. This figure is inspired by another figure from Devrient and Lambiot on a discrete curvature on graphs from the effective resistance, which occurred last year. So these are kind of the canonical examples of curvature regimes in graphs. Now, here are some examples of how the laziness parameter changes the way different graph structures are attenuated, and I hope this also works on your monitors at home. But what you should see is that if we increase the laziness from 0, which means that we never stay at our node, so we are completely unlazy as a random walker, to 1, which means that we always stay at the same node, you will find that the curvature converges to a positive value, so to a very to a higher value. Whereas with lower values of alpha, we see some difference, we see some negative curvature values in the graph. But despite, if you remember the colors from the other Forman-Ricci curvature dataset, the differences are a little bit more subtle here. But nevertheless, this tells you that you have some kind of lens through which to view your graph in various ways. Now with this, I'm at the end of the, I would say, of the introductory part, and I would now like to talk about 2 applications of these curvature notions. One is a little bit more theoretical than the other, but we'll stop. We'll first start with the more applied one. Are there any questions or common discussions items at this point?
Bastian,
hello.
Oh, sorry. Please go ahead.
Yeah.
Yeah, Bastian, if I can ask, can we go to that Bonnet-Meyer result?
Yeah. Should I go back to this? Yeah.
Yeah, yeah.
Mm-hmm.
So I was thinking whether a distinctive study of those graphs have been made, where these quantities dij and diameter of G attain the bound.
That's a good question. Honestly, I'm not sure. I think, let me jump one slide ahead. I think the paper by Lin and colleagues of Ricci curvature of graphs has some examples of this. So I know for sure, I didn't include this here, but I know for sure that that Lin and colleagues are looking at certain prototypical spaces, so regular graphs and fully connected graphs and these sort of things.
Okay. Thank you.
You're welcome.
Bastian, Renzo here. I also have a little question or clarification. You seem to hint that laziness could be associated with a flat situation, zero curvature. Is that correct?
What I want to say with this is that if we pick the laziness parameter, so if we let the laziness go to the very limit, then at a certain point we only have these Diracs, right, that we are comparing. And I think in this case, what you will find is that the curvature should actually be zero throughout the it should be positively curved throughout the space, I would say. Maybe I said that incorrectly.
Oh, okay. Thank you.
You're welcome. But wait a second. Maybe let me briefly think about this. I can also get back to you later on this. But I know that there are certain kind of limit theorems that can be made. But my point that I wanted to make with this slide was more to say we have a kind of parameter that we can adjust to attenuate or to improve or express certain parts of the graph a little bit better. So it's not a priori clear how the laziness should be chosen. That is my point. Maybe the limit values are not the greatest examples here.
I was just wondering if laziness can really be associated with the particular regimes of curvature, like curvature equals zero rather than different from zero. That's all.
I see. Okay. Yeah. I think overall this also goes back to the point that I wanted to make with this first slide here, namely that there is no strict choice in these probability measures, right? So no one forces you to choose a specific measure. So all the results have to be kind of contingent. Either they have to apply to all measures, or they have to be contingent on a specific choice of measure. So this is kind of where it will later be also interesting in our hypergraph curvature analysis, because there we were looking very deeply into how to pick different measures correctly. All right, then let me briefly move on to part 4 on the comparison of graph generative models. So here we need to take a brief step back, and I want to briefly tell you about this problem and why it's relevant. So in graph distribution comparison, we are assuming that we are given a distribution of graphs, so some script G, which could be set of graphs G1, G2, and so on and so forth. Moreover, we also assume that we have different models for generating new graphs. So I can take these models and generate a new distribution, script G prime, that generates a sequence, maybe the same number of graphs, or maybe even more, or maybe less, of new graphs. And we then want to know how close or similar in the distributional sense these two distributions are. This might sound a little bit constructed or artificial, but it actually is a very important problem in numerous application areas. For instance, in drug and molecule design, where it's always important to take, for instance, a database of drugs and molecules where you already know that they work, and now you want to train a machine learning model to generate new ones. Similar to these large language models that are supposed to generate new texts or new poetry or whatever, you also want to have new generative models that might lead to new drugs, new molecules, and so on. And then there's also, of course, things like road networks, which might be interesting to compare and analyze for different for city planning and so on, and vessel networks in for instance, organs of human beings. So there's a lot of diseases that are associated with our eyes, for instance, where the vessel structure breaks down over time. And so having a way to mimic these kind of distributional processes is very important. The way I present this problem here, I should say this is very hard to solve in practice, and there's a lot of hidden pitfalls behind that. So I will make a very, very bad job in introducing this, to be honest, because there are very subtle and very nuanced things to do. But I wanted to tell you at least how curvature can maybe help with some more time and some more experiments in this realm. But please feel free to contact me, of course, because we've been looking at this from different angles now for a couple of years, and it's really fascinating. Anyway, what I want to briefly present here is a new curvature-based comparison workflow, which is a current preprint of ours. It's a joint work with Josh and Jeremy and Michael. And the central premise of this workflow is that since we consider curvature to be some kind of multi-scale phenomenon, so it's something that is local, but it can also be put on a global level, we also need descriptors that are inherently capable of leveraging this multi-scale structure of a graph. And this then, of course, leads me, because I very much care about this and enthusiastic about these TDA kind of approaches, but this then leads to immediately, for me, ideas from persistent homology to use those on the graph. And here, I apologize to those parts of the audience that are not super familiar with computation topology. I will do a very, very quick overview, but it might not be direct. It might not be enough, but I'll try to at least illustrate some of the nicer properties. Namely, we essentially borrow in our proposed pipeline for this graph comparison, we borrow ideas from persistent homology, and we use curvature as a filtration function on the graph. This is something we'll see on the next slide. The advantage of why we're doing this is that if we translate the problem of comparing graph distributions into the problem of comparing topological representations of these graph distributions, then we have made the problem much, much simpler, because the topological representations, they permit very simple representations. They permit very simple calculations in terms of statistics. You can, for instance, calculate a mean quite easily, and so on and so forth. All of those things are not necessarily given on the distributional level. So given 10 graphs, there is no easy way to create an average graph, but given 10 persistence diagrams or 10 different topological descriptors, it is possible to generate some kind of mean diagram or some kind of mean descriptor. Now, what we do in practice here, what we propose doing is based on a three-step program in a sense. Namely, we first calculate persistence diagrams based on curvature filtrations. We then convert these persistence diagrams into more suitable representations. So again, if you're familiar with these sort of processes, then this might be already very straightforward for you. But for those that are not, the persistence diagrams that tumble out of this, we'll see a couple of examples in a few minutes. They are a little bit of cumbersome to work with, so it's much easier to convert them into a curve-based representation or a piecewise linear landscape representation, something like this. And finally, once we've done this, we can compare the respective representations using, for instance, permutation tests or averages or distances and so on. Now, what is actually filtration? So let me at least give you a brief overview of what it is that we're doing. So a filtration of a graph uses a scalar valued function on the graph. It can be defined either on the nodes or on the edges or in both. In our cases, it will be an edge-based filtration, but we can make this work. We then obtain a natural filtration of the graph, that is a sequence of nested subgraphs, by analyzing, for instance, the pre-images of F. This is also known as a sub-level set filtration, because we increase our threshold from a very low threshold to a very high threshold. And as you can see, we start with the full graph here, and we assign it a function. We look at the function values at the sub-level set for value 0. We have nothing there. We increase it a little bit. We have now these 2 points here. We increase a little bit further. We now get those edges as well. And finally, with the highest value, we have reconstructed or recovered our full graph. And this only requires a scalar valued function on the graph, so it is very easy to accomplish, and moreover, it is computationally very efficient, because we're just dealing with all the nodes and all the edges in the graph. There's nothing higher order going on, in case you're familiar with simplicial homology, for instance. We're not using any higher order information here yet. Now, this gives us a way to calculate topological features. And again, I can only briefly allude to this, because otherwise this would be a completely different talk now. We would have to discuss persistent homology. But alongside a filtration, we can calculate topological features, that is, in our case, connected components and cycles. And this will then lead to multi-scale topological descriptors, also known as persistence diagrams. And these persistence diagrams, they tell us how the connected components and cycles of the graph change with respect to the sub-level set filtration parameter that we pick. And of course, since it's only a finite number of edges, there's also only a finite number of critical values where this changes, so we can actually do this in practice. Now, these persistence diagrams, unfortunately, they form a metric space, But luckily for us, they also afford representations in some kind of Banach spaces, which then also give rise to statistical analyses. This requires then some kind of transformations into either something like a Betti curve or persistence landscapes. Apologies, I'm unable to show all of these things here, but let's just say that we take these descriptors, we transform them in a nicer fashion, and then we can calculate averages or distances in this space. We can also do a lot of things in the persistence diagram space, by the way, but the mean representation is a little bit harder to get. There is only Fréchet means if you're familiar with this terminology. But I don't want to spend too much time on this. I just want to show you two brief results that I find interesting before then jumping onto the hypergraph part of the presentation, which I'm looking forward to most, to be honest. So the curvature filtrations that we get from these graphs directly, they are very expressive. Expressive in the sense that they give us a way to distinguish between different types of non-isomorphic graphs. And in fact, we can even show that this distinguishing property is even better when we use the curvature values in a filtration setting than when we use them in a raw setting, so as just a descriptor of the graph. Now, the exact specifics of these experiments are not relevant here, but I just want to point out that if we use different data sets which consist of strongly regular graphs, which are really hard to distinguish for other methods, then we find that if we start with the raw value, so with just the distribution of curvature, there are certain times where this doesn't work at all. So for instance, this last data set here, but if we use it in a filtration setting, suddenly this expressivity goes up quite considerably. Of course, you can also see that there are certain types of strongly irregular graphs which, for whatever reason, we cannot really distinguish any better, but at least we're seeing some minor improvements. So that at least points for me, this points towards the general utility of Olivier-Ricci curvature in this setting. And likewise, and this again, I don't want to spend too much time on this because it is very, very much preliminary in some sense, but what we also see is that these curvature filtrations can help in counting substructures in graphs. So counting substructures is a very important task because if you have availability of these substructures, you can easily also decide whether one distribution of the graphs is better or similar to the original distribution than another one. And it turns out that Olivier-Ricci curvature in a filtration setting, I should also say, is very good at counting triangles and tailed triangles, and it's less good but still better than the raw values in counting stars and 4 cycles. So this is also a very interesting result which we hope to expand later on. This is very, very empirical at the moment, but we hope to also provide a more theoretical view on these things. Now, that already brings me to the final part of the presentation, which we'll revisit curvature. So when we put everything together that we have just seen and develop and extend these measures for hypergraphs. Are there any questions so far before we go into this last leg of the journey?
Just one question. In the previous slide. That table that you have right there. How do you use the filtration to count triangles and tailored triangles and all this stuff?
Yes, that's a very good point. I left that a little bit out for the sake of simplicity. But what we are essentially doing is we're solving a regression task, and we're using. So we have a target value for the respective graph. So for instance, the graph might have 5 triangles and 6 tail triangles or whatnot. And we use the filtration, the persistence diagrams in a predictor to make this prediction, to make this to calculate these regression values. So it's in machine learning terms, it's a classical regression task.
Okay, thanks. It's just a classical technique.
Yes.
With mature learning. Okay, so those numbers that you have there is the percentile of accuracy, or
it is a mean. It's a mean average error. So lower values are nice, and ideally, ideally this would be 0. Yeah.
Okay. Well, thank you. Thank you very much.
Yeah, You're welcome. I mean, there's also more. I'm really happy to discuss this more later on. I wanted to give you some kind of overview of why this technique might be useful here. But of course, there's, as I said, there's hidden nuances there, and we can discuss more how this training was actually done and so on.
I understand. Thank you very much.
Right. All right, then let's go to the last journey. So here we are going in another direction entirely. We're going in the direction of hypergraphs. So this is recent work with my wonderful collaborators Corinna and Sebastian, and it's currently in press to appear at ICLR 2023, which is a machine learning conference. And essentially what we're doing is we are proposing a new framework or a joint framework for Olivier-Ricci curvature on hypergraphs. Before we delve into this, let me illustrate why hypergraph is actually useful, and I'm very happy that this is being recorded here, because many times when people are looking at, for instance, co-authorship networks, they tend to look at just the graph. They're just saying, okay, two authors get an edge if they published a paper together. But it turns out that if you do this, you actually miss a lot of the structure that you could get otherwise. So if we treat this as a hypergraph problem, then we have a little bit more leeway here, and we can set up our representation a little bit better, because in a hypergraph, a hyperedge may be any kind of subset of the vertices of the nodes of the hypergraph. So in some sense, graphs can also be seen as special cases of hypergraphs, right? But we can have hyperedges that have 3 nodes, 4 nodes, whatever. And as you can see from this simple example, which is something from my own co-authorship hypergraph, is that hypergraphs capture higher order relationships way better than ordinary graphs. Because, for instance, I published together with Philip and Kai, but Philip and Kai never published together with other people here. So outlining these type of relationships is really, really critical, because you can't see these type of click relationships or these type of lab relationships almost by just looking at the graph. Now, this is just one example. Of course, you can build hypergraphs out of many things, and we'll see some examples later on. But of course, when we generalize curvature to hypergraphs, there is the big question of what we should actually do. So how do we accomplish this in practice? And what I'm going to show you next involves a certain type of non-canonical choices. So I'm really open and hope that we can discuss a little bit what you think about these choices. Now, for your memory and for your recall, on the left-hand side, I'm showing the ordinary, I should say, graph Olivier-Ricci curvature, where we have the Wasserstein distance, our probability measures, and the distance. And now on the right-hand side, this might be a little bit more complicated. So what we came up with, what we think might be a good generalization, is that we actually assign this also to a hyperedge, so just a set of vertices of a hypergraph, but we change it a little bit. We set an aggregation function here, which we'll define in a minute, and an overall distance of the individual edges. So we assume that we have some kind of underlying graph structure still in the graph in which we can do the distance calculations, and then we just assign this distance to be the maximum of all the distances in that edge. That seemed to be a relatively reasonable choice to make, but only since we thought about how to do this aggregation in a formal fashion. So this aggregation function should still take the place of the Wasserstein transport distance, but it must by needs be a little bit more complicated, because a hyperedge can consist of any number of vertices. So there is no kind of predefined or prescribed calculation of the Wasserstein distance between several probability measures anymore. Rather, what we have to do is we have to go somehow over all of them. And we have a bunch of aggregation functions that we thought about. We describe at least 3 of them in the paper, but here I'm only going to show you 2 of them because they're the easiest to describe. The first aggregation function that we developed is the average aggregation, which does what you might expect it does, namely it takes all the pairs of vertices I and j that are in this hyperedge, and it just calculates the Wasserstein distance over the respective probability measures, and then later on it just averages this out. There's a factor 2 here because this needs to be symmetrical and so on. The other notion that we have is even a little bit easier, and I have to say personally I like this maximum aggregation function even more because it somehow sends us to the worst case always. So in the maximum aggregation function, we just take a look at all the subsets again, of all the subsets consisting of 2 nodes I and j, and we just calculate the Wasserstein distance between the respective probability measures, and then later on we take the maximum. So again, this is a plug-and-play choice, so you can pick your different aggregation function here, but it should be something that ideally incorporates calculations made over all the probability measures that you can do. Now, the second point that we have to think about here, and this is also where the name of our paper, Orchid, comes from, is that it kind of looks like a flower if you just look at this, right? It is really beautiful, and this is what we want to illustrate with this beautiful illustration is that we have a different choice in choosing probability measures or in doing random walks over this graph structure. So given a hypergraph with a simple neighborhood of this node 0 here, there's a couple of things that you can do in a random walk or in defining a probability measure. You can, for instance, do the simplest thing and just visit all the nodes that are part of that are reachable from this hyperedge with equal probability. We call this the equal nodes probability measure or the equal nodes random walk because, as you can see, everything is being treated equal. What you could also do is you could visit all the edges with equal probability, and then furthermore choose one of the nodes in the edge at random. So you first pick an edge here uniformly, and then you pick one of the other nodes in the edge. And the last one is you could pick the edges in a weighted fashion, so you could divide your probability mass depending on how many shared intersections there are or how many points there are in the edge entirely. And as you can see, I would say there's no canonical choice for this probability measure here. So already going the route of the more structural description of the hypergraph, we have to decide how we do these calculations in practice. Now, before I show you some very nice preliminary results, I want to briefly mention some properties of hypergraph curvature that we were already able to show in this paper. So first of all, we have a very natural, consistent setting in the sense that we can show that hypergraph curvature is respectively negative, 0, or positive for hypertrees, hypergrids, and hypercliques respectively. So in some sense, we retain this comparison space that Olivier-Ricci curvature has, and that furthermore ordinary Ricci curvature on manifolds has. So we have these 3 distinct regimes, and they correspond to 3 distinct classes of hypergraphs. We also have very simple lower and upper bounds for the curvature of an edge in terms of the total variation distance between probability measures. So given a hypergraph and these probability measures, we can already give you some inkling in which space, in which realm, in which interval your curvature might lie. And last but certainly not least, we have this relationship again between local and global properties of a hypergraph. So we again get some kind of Bonnet-Myers-like theorem. This time it is a little bit more complicated, unfortunately, so we're not going to cover all of that, but the important equation is this guy here. So the distance as we define it, so this maximum distance over pairs of points of any subset of nodes. So again, this pertains to all the subsets of nodes that we can build, not only the hyperedges, right, is less than or equal to this jump probability. So again, this is this term of the distance between a Dirac mass and a probability measure divided by the Olivier-Ricci curvature of the subset. So again, we see that in particular we are able to retain and restore the diameter bound of a hypergraph here as well. This is really, really astonishing. It needs, however, I should say this, it's not a nice theorem at this point because it has some kind of technical assumptions. So we need this assumption that we know that the aggregation function is kind of monotonic. This is not a nice assumption to have. It is satisfied for my favorite aggregation measure, but it's not satisfied for all of them, unfortunately. So clearly there would also be a lot of work to be done now for figuring out how to extend this to other settings. But that being said, I want to show you hopefully 2 convincing examples of what you can do with curvature and then kind of outline where to go with this. The first is what we found is that hypergraph curvature is really, really discriminative. So it's not something that is just doing some relatively strange calculations that are non-canonical on the nodes and on the hyperedges respectively, but it really gives you an insight into different types of hypergraphs. So for instance, here you can see hypergraphs that are built based on authorships of the American Physical Society papers, and different collections, so different journals, for instance, exhibit distinct curvature patterns. So the left-hand side is for the equal edges probability measure, the right-hand side is for the weighted edges measure, but you can see that these probability measures are a little bit different all the time, which is good, which is as they should be, but also you can see that these profiles are really, really different. So, and this really, when we look into this, when we look at the hypergraphs that tumble out of these journals, we really see that the citation culture of a specific journal and the co-authorship culture, I should say, is really different. So this is really a very, very nice find without necessarily going too deep into the modeling aspects of these hypergraphs. Second, and this is also very exciting, if we build hypergraphs based on questions on certain forums. So we take specifically we take questions from Stack Overflow forums, and we look on the tags that are being given to these questions. So the vertices of this hypergraph are the tags, and the edges are the respective questions. So every hyperedge is a question that is being asked. Then we find that even a very simple curvature calculation with one of the aggregation measures leads to almost nicely interpretable embeddings almost out of the box. So specifically, we use an RBF kernel here between 2 distributions of curvature values, and then calculate embeddings using kernel PCA. So kernel PCA is a method for visualizing or embedding kernel matrices, so dissimilarity matrices of general data sets. And if we later on annotate all of these questions, so every point here is a question that is being asked in the forum. If we now annotate this with different types of categories that we assign based on the forum which this was asked in, then we find that there is a very nice clustering structure almost immediately. So we have a cluster of religion topics that are relatively nicely related to maybe the Latin languages here. We have a cluster of well, we call them nerdy topics with role-playing games, board games, and so on, which are also a little bit removed from the language cluster, except for maybe these role-playing games here for whatever reason. And then we have a large cluster of languages. So again, this is really just tumbling out of the curvature calculation and is not something that we specifically put into the modeling of the equal edges random walk. So the point I want to make with this is that we can really get new insights into hypergraphs, but at this point, it is very much unclear what we can leverage those insights for, or where we want to go with this. So do we want to classify them, or do we want to make certain prediction tasks, and so on? In the absence of these tasks, so in the absence of knowing where to go with this in terms of analysis, we opted for making rather a big smorgasbord almost of different ways of representing curvature, calculating it, and showing that these values are actually distinct. Now, this brings me to the end. I want to start a discussion with you. First of all, I want to mention a couple of limitations in the last minutes that I have. So one issue that we have with both hypergraph curvature and graph curvature is that the calculation does not necessarily scale well with the increasing number of edges, because you need to solve a lot of optimal transport problems. It's doable. It's not infeasible, I would say, but some smarter approximations, some smarter guesses are definitely required here, I would say. Moreover, curvature is also, in the way we currently set it up, is oblivious to attributes of the respective hypergraph. So if we have additional attributes in our graphs or in our hypergraphs, we have at the moment no way of dealing with that. And likewise, we are only working with very localized probability measures. There might be a reason for this, but still I want to mention it as a limitation. Now, so to summarize, I hope I have convinced you that curvature is expressive and useful for graph learning tasks. It provides a complementary multi-scale perspective on graphs and graph distributions. And I want to stress that even in the more structured setting of graphs, there are several non-canonical choices that had to be made. So we really, moving forward, I would really say we need to study their implications a little bit more detailedly, because otherwise it's a little bit unclear what we're actually looking at. And with that, I'm at the end, and I thank you very much for your attention and hope that we have some time for a little bit more questions, although I already appreciate the discussion that we had in between very much. Thank you very much.
Okay, Bastian, very good. Thank you. So questions, please.
Well, I got a little question. It's just probably you mentioned this before, but I don't know if I got it. And just want to make sure what happened with, would you just have how to put this question? Do you have a curvature defined on graphs and a curvature defined on hypergraph, right?
Yes.
So, well, I'm trying to imagine that there is a really close relation between those two. For instance, I was thinking if you take for the graph, you just take the I don't know, the click hypergraph. Does it give you any extra information about the renal graph to computing the curvature of the click?
That's a good question. So, yeah, I'm not sure whether I fully understood this, but what I can tell you is that we have checked that the hypergraph representation actually contains more information than the graph. So we would also expect that the curvature gives us more information. Okay. However, in the other direction, what we have also shown, and I think this is really relevant in terms of talking about these non-canonical choices here, and this I haven't mentioned at all, I'm sorry for this, but we have also shown in the paper that if we go from a hypergraph back to a graph with our hypergraph curvature notions, then those just become the ordinary Olivier-Ricci curvature again, which I think is really important to have. So for instance, if we, sorry for the jumping, but if we look at this representation here, or at the maximum aggregation, if you only have normal edges, so if all your hyper edges are normal edges of a graph, then these will automatically become the usual Olivier-Ricci curvature expressions. Oh, so in that sense, I'm not sure whether this is what you were looking for, but in this sense, the two concepts are at least somewhat related. Yes.
Yeah, I was thinking more in the other direction. And like, if you start with a graph, and you create the click hypergraph, yes, like the one that you put extra faces, right? And you compute and then you compute the curvature for this new click graph. Is that going to give you any extra information if you just compute the curvature from the renal graph, the regular curvature, or is just the same value? Is give you the same value for the same information? Is more like the direction. If it works, if it were something to just move to the click structure.
That's a very good question. I cannot give you a straight answer, unfortunately, here, because we haven't actually looked at this. So our experiments were coming from the wrong side in that sense, because we were rather saying, here's some data. We believe that this data is best modeled as a hypergraph to begin with, and then we studied the hypergraph. But what you're describing is really exciting. I had not considered this before. Very. It's great that you mentioned this. So what you're proposing is taking the graph, then doing the clicks, for instance, and then building a hypergraph based on the clicks, right?
Yeah, exactly.
Yes, yeah. So, okay, this is exciting. I'm not sure whether we would see more there because in some sense the graph already no, the graph doesn't contain information about its click necessarily, right? But honestly, we haven't studied that. That would also be very interesting because we haven't looked at simplicial complexes, for instance. So,
Simplicial
of course,
complexes. Okay.
yeah.
Uh-huh.
I mean, a simplicial complex would, of course, also be calculable with this approach, right? But still, we haven't actually did those. Yeah.
Okay. Well, thank you. Well, thank you very much for your answer. I will be hoping that the answer will be like it is kind of uh you will get the same information or not much is going to be changed in terms of curvature
Yeah,
information. Yeah.
that
Um,
would be interesting.
but yeah, that will be interesting to analyze. Thank you very much for your answer, Bastian, and
Yeah,
excellent
thank
talk.
you.
Yeah, I really enjoyed
Thank you.
it.
Thank you. Yeah. Please also thank you for this inspiration. So feel free to reach out to me. I'm happy to discuss this further. I mean, we hadn't considered this. We kind of find it hard to be honest to pick the direction that we should take because there's so many interesting directions in the hypergraph setting. It's there is some work already ongoing, right? But making doing this in a compelling framework way where we kind of understand where we have an underlying program in some sense, this is really new to us. Sorry. Yeah. I'm excited about this.
Good.
Sure. Mhm. Yeah, go ahead, Francois.
Sorry, I think there was another question, right?
Any other question from the audience? I might have just a curiosity again, Renzo, here. Sorry,
That's good.
Bastian. Is in curve, considering space curves, there are problems that involve a little, well, they inherit aspects from physics, and you associate, for example, to each point on a curve in space some aspects of dynamics. For example, curvature along the binormal to the curve, or curvature along the normal, principal normal to the curve. And then you study the dynamics under some relaxation of this problem, energy or whatever. Do you have anything similar, physically inspired, that would associate information to curvature, and then eventually associating some dynamical flow on each on the graph you're considering?
No, unfortunately not. But that's a very exciting thread. I really have to think more deeply about this. But if I understand you correctly, what you're proposing is that one could develop new curvature notions based on such flows on the graph, right?
Exactly.
That's really exciting. No, I
Since,
have to. Yeah, haven't
since,
considered this.
since curvature flows play a very intriguing and interesting role in space curve dynamics, because to some extent simplify but still mimic dynamical features of field vector lines, etc. I would bet that associating similarly dynamics with curvature on a graph would be quite interesting, would open up very interesting areas of research.
Yeah, no, absolutely. I mean, probably the wrong direction here, but from what I understand. But what we are also looking for at the moment is how to extend these notions to graphs and hypergraphs in particular that vary over time. So there's you could think about having some kind of dynamical process that deletes an edge of the graph or that creates new edges and so on, right? And studying the behavior or the changes of curvature under this, I think would also be interesting.
Okay, thank you.
Of course, yeah. You're welcome.
I have a question.
Mhm.
Yeah, thank you. In the case of when you compare the co-authorship networks of the
Yes.
American Physical Review, did you know what is the difference, or did you compare with a classical measures like clustering coefficient or something like that in classical networks? And did you know what is the difference or the advantage, or did you find some advantage of this?
Yeah, so this is a very good question. I don't know everything by heart at the moment here, but what we did is we compared to existing network measures as well, and we found that curvature carries more information than those. But I want to stress that when I show you this graph, this doesn't necessarily mean that we are the only ones picking up on that difference. So as far as I understand, since the field of hypergraph analysis as such in machine learning is relatively young, I would say, there are, I think, no results of the form where we can say this is the only method that can do this, right? So hence this is more of an almost experimental mathematics in the sense that we try to define these notions, we try to see what properties they have in practice, and then we try to see what we can do with them. But yeah, I want to stress that this doesn't mean that normal network measures are necessarily bad. It just means that they might pick up on different aspects of the data.
Yeah, thank you. I understand that was the point, but I only feel curiosity to know if you did this kind of comparison. But yeah, thank you for your answer.
No, you're welcome. We did a couple of those. So the appendix of this of this publication is really long now, and we're continuously adding new results. I just don't know by heart, to be honest, whether we already have the new results with clustering coefficients or with network-based measures in there. But that's a very good point. I mean, yeah. Back to the last slide again.
Other questions? If not, okay, we'll bring this beautiful meeting to a close. Thank you very much, Bastian, for a beautiful talk. Thank you. Thank you.
Thank you very much for having me. It was a pleasure.